Hello everyone, welcome to this channel, welcome to this video. I'm Saptarshi Mukherjee. I'm a software engineer 3 at Google and I'm a computer programmer. So in this video I'm going to focus on 4 problems of Codeforces Round 932, the problem B up to the problem E. These are the 4 problems I'll be discussing in this round, and I'll be discussing not just on my own solutions but also on tourists' solutions. So this round is a bit special to me because this helped me become a candidate master after a good time. I had become candidate master a number of times, as you can see. I had stayed a candidate master for a good time, but then after a long time, I had lost my streak, etc. So it brought me again back to candidate master. And apart from that, I'll be discussing also on the solutions of tourist, showing that in what ways he has done few things better than us, and we will try to learn some things from his solution. So for some of you who are actually new to computer programming, here's who tourist is. The legendary grandmaster Gennady Korotkevich, an excellent programmer, an excellent computer programmer. He is from ITM University. So as you can see, he has stayed on top for a very good time. And if you look at his coding period, he started coding around 2010 and he has been coding even now, 2024. So that's the range that he has actually kept himself going. 10 years, or it's 14 years. It's 14 years or more than that that he's actually actively coding. So that's the best part. And you can see over here, if we zoom in, we'll probably see ups and downs, but a great coder to follow, a great coder to learn from. And that's why I'm using his submissions in this video totally for educational purpose. So let's get started. This video is not about any comparison kind of thing between his solutions and alternative solutions, etc. We are just going to see the few things he has done differently, what probably we might have not thought about doing, and we'll see how we can learn from some of those things and grow ourselves as better programmers. So yeah, let us look at the first problem for today. Informatics in MSc. It basically says that you are given an array of length n, and then you have to divide it into k subsegments where k is greater than 1, such that the MEX on each subsegment is equal to the same integer. MEX basically is the smallest non-negative integer that is not there in the array. So from 0 it starts. If 0 is not there in the array, 0 is your MEX. If 1 is not there in the array, 1 is your MEX. So we have to split into subsegments such that MEX of each subsegment is the same integer. So then we have to return that. This is the format. Yeah. So let us take maybe this example, 017101003. 017101003. So we can see over here that the first two, if I take, this gives me an MEX of 2 because 2 is the smallest number that is not present here. Over here if I see 7 is present, 1 is present, 0 is present. So smallest number that is not present. What are not present? 2, 3, 4, 5, these are not present. What is the smallest non-negative number that is not present? It is 2. It is 2. If I just look at this one, what is the smallest? What is the MEX in this part? In this part only? It is 0. 0 is the smallest one that is not present. Here, if I see among these two elements, 0 and 3 are present. So 1 is the smallest element that is not present. So this is the definition of MEX. 2, 2, 0, 1 are the MEX of these parts. I want to split in a way that the MEX of each part is the same. So the first two were good, 2 and 2. The last two are not good. I mean, not the same as these two. So we'll try to look at it differently. We'll say, okay, if I take them together, 1, 0, 3, then 0 is there, 1 is there, 2 is not there. So from the beginning, from 0, we will see which is the first number that is not there. So yeah, in this way, we have the same MEX. We will say, okay, the answer basically is 2. And yes, it is possible to split it into these 3 parts. We will basically provide this. We'll say that, okay, from here to here, then from here to here, and then from here to here. These are the 3 parts. That will be our answer. Now, how to solve this problem? First of all, what will be the MEX value that we will try to uh, you know, create subsegments having that MEX value. So what will be that MEX value? We know each subsegment has the same MEX value. Each has the same MEX value. Let's say X. What will be that X? Will it be 1? Will it be 2? Will it be 3? How can I understand that? Let us understand over here. Can I say in this part, in each of these parts, 2 is not there? So can I say in the overall array 2 will not be there? I know that in each part 2 is not there, that means 2 will not be there in the overall array. In other words, let's say I have an array, I divide it into few parts, each part let's say has MEX X. For that, what is necessary? If X is MEX, that means in the whole array X is not present, because X is not present in none of this, X is not present in any of the segments. So I can say that X is not present in the whole array. That is the first point. Second point, before X, is everything present? Can I say since X is the MEX in the first segment, that means from 0 to X minus 1 everything is present? And can I say that 0 to X minus 1 everything is present in the second part as well? And in the third part as well, can I say that 0 to X minus 1 is present? And when I know this, that 0 to X minus 1 is present in each of them, definitely my whole array contains 0 to X minus 1. So 0 to X minus 1 is contained in the array, whatever is the array. So X is not there, 0 to X minus 1 are there, which means that if X is the MEX of some subsegments of my array, X is the MEX of each of the subsegments of my array that I'll be creating, whatever are the subsegments, then X is also the MEX of the whole array. X is the MEX of the whole array. And what does this tell me? This tells me that if I find the MEX of the whole array, so the first thing is, if I find the MEX of the whole array, that will give me that X, which I have to now split in such a way. I have to split this array in such a way that each part contains MEX equal to X. But I'll get the X from here. I'll get that important X from here, which will become the MEX of each of the parts. I can't find any other thing. I can't split in such a way that X minus 1 will be the MEX of each part, because we know that X minus 1 is present in the array. So X minus 1 will be present in at least one of them. X minus 1 can't be my answer. Similarly, I can't expect X plus 1 because X is not present, so X will be the MEX. So I know that, okay, I have to divide in such a way such that each part contains X as the, will have X as the MEX. So first part is done. I know what is the MEX that I expect. So then, what can be the second step? You can say it's a greedy algorithm. It can be understood trivially that if this is your array, what will be my first subsegment? Let's say I want to form my first subsegment from the left. From the left, what does my first subsegment need to conform to? What is needed here? It should not have X. We don't worry about that because X is not there in the entire array. So yes, for the MEX to be X, X should not be present, but X we know it will not be present. Next, everything less than X has to be present, right? So that something else doesn't become the MEX. So this should contain all the numbers from 0 to X minus 1. That's it. So iterate from the beginning, keep on taking elements one by one. Take the first element, take the second element, third element, and so on. When you find an element, at a point when you see all these elements are there, some element can occur duplicate number of times. So if you see all the elements are there, that means you have got the first subsegment. You can't take the smaller first subsegment as smaller than that. You can't take a subset of this, maybe part of this. No. Because if this is the part where you basically said, okay, up to here I got all the elements. Before this I did not get all the elements. So the first task is you have to create the first subsegment which will contain all the elements up to X minus 1. The moment you get that, you will say, okay, this is my first subsegment. I'll finish over here. It can't be smaller than this because in the smaller subsegment you won't have all the elements. The moment you get all the elements, you will say, okay, now stop. This is the ending part. You will not take more elements. Why? Because you want to leave the space for other subsegments. You want to have other subsegments. That subsegment also has the same requirement. It needs everything from 0 to x minus 1. So can we say that the more space we leave after this line, the more space we leave, that is easier, that makes it easier to get all the elements in the second half, which basically tells me that okay, first half needs to be not larger than it requires to be. We should not make it larger than it requires to be. If we consume too many elements in the first half, second half will not have sufficient elements to cover its requirement. So we should take as many elements are required here. So you will keep a structure which will keep on telling us whether these elements are obtained or not. All these elements, we can keep a set kind of a structure. And for the second half, we will keep on forming that okay, from here to here, is it contained or not? Does it contain all these elements or not? If it is contained, let's say I know that okay, from here to here, halfway, it contains all the elements 0 to x minus 1. I can say okay, take the entire thing. This means that the entire thing also, from here to here, the entire thing also contains everything from 0 to x minus 1. So if this orange part contains 0 to x minus 1, then I can see yes, the entire thing will also contain 0 to x minus 1. So yeah, that is the logic. That is the logic that I employed. That okay, find out that MEX, then try to form the first subsegment. That will be very clear. First smallest subsegment. This is the first smallest subsegment. By first, I mean that it will start at the 0th index. And smallest definitely makes it deterministic. This is where it will end. If you take one step before, you will not have all the elements. So you will take the smallest and then the remaining you just have to measure does it have all the elements, then it will become your next subsegment. That's it. So here also let us apply the same thing. We will say okay, in the whole array the MEX is basically 2. And how can we find out the MEX? We can first of all store all these elements in a map kind of structure, and then from 0 to n or n plus 1 we can go from 0 to n, and we can say okay, for each element see if it is contained in the set. If it is not contained in the set, the first element that is not contained in the set is my MEX. So I stored these in a map. In a map, let's say I have 0, 7, 1, 3. I have all the elements. Now I'll check one by one. I'll check okay, 0 is there, fine. 0 is not the MEX. 1 is there, okay, fine, not the MEX. 2 is not there, that means 2 is the MEX. So in this way I'll find the MEX. Next thing I'll say okay, now from the beginning try to find out the smallest subsegment that does not contain the MEX. 0, 1. Sorry, that contains everything before the MEX. 0, 1. And then I can say okay, the remaining part, let us see 7, 1, 0. Okay, everything is finished. I've got the MEX once again. I mean everything before the MEX has been taken. So I'll just say now continue this. Just combine this into this. So this becomes one subsegment. This is one subsegment, smallest one from the left. This is the last subsegment. You just have to see whether it contains everything. So yeah, that's pretty much what I did. If I show my solution, yeah, I used a hash set. Don't go by variable name. I used a hash set and I have added all the elements. Then from 0 up to n plus 2, you can go only up to n. So this needed to be n plus 1. Just for security measure, I put n plus 2 so that I'm not missing a case. I'm checking if it is not there, then that is what we are looking for. I'm just breaking. So I contains that element. Now I'm storing that I in F. So F basically is that MEX. Now I'm using a different set 1. I'll say okay, this is where I'm going through from the left. I'm seeing that okay, if it is exhausted, so basically if AI less than F, set1 dot add AI, and then I'm checking whether set1 dot size is equal to F, and then I'm breaking. So basically if I have that many elements in my set, then I'm breaking. So this is one thing that you can note, that if your MEX is 2, that means Before 2 you have all the elements. Before 2 you have how many elements? 0, 1. What is the size? The size is also 2. So whatever is the MEX, the size of the previous elements, the size of the number of previous elements, or the number of previous elements is going to be also the same as the MEX. So if x is your MEX, we can say from 0 to x minus 1, the size of this set is also x. That is also the MEX. So this is quick implementation thing, that okay, if set 1 dot size is equal to MEX, or sorry, f, that thing, then basically break. That means, and what am I adding in this set? I'm basically adding AIs. So if AI is less than f, then add it. So which AIs? Only those that are less than the MEX. I'm not adding all the AIs. I'm adding only those AIs that are less than f. And I'm saying okay, break. Next, I'm basically checking that okay, if you have run through the entire loop, that means you did not find. This will not happen, by the way. This condition will not happen. Now I know that. But anyway, what this is telling is if you have run through the entire array, then you don't have space for the second subsegment. So then -1, basically we don't have such a split possible. Otherwise, G is equal to I. What is this G? G basically is the position from which you will now continue. So at ith position, you basically said that okay, we are done. We basically broke. And G is that position up to where you have already seen. Okay, now I've taken I plus 1. I probably would have wanted G plus 1, but okay, I've stored the G for later, for this point. So from I plus 1 to n, I have now gone and done the same thing. So in the second subsegment also, I'm basically checking from I plus 1 up to the last, that whether I'm able to finish or not. If I'm not able to finish, then -1. If I'm able to finish, then I'll say just split into two parts. One to G plus 1 and G plus 2 to n. And that's exactly, that's very similar to what Tourist has done. The amazing part is that if you can see, Tourist has actually, the top row refers to the Tourist. He has finished the coding it in actually 2 minutes. And not just coding. He has read the question, understood, implemented everything. He has done in 2 minutes. And he has submitted the code. So let us see what differently he has done. Okay, not that smaller code. So definitely typing needs some appreciation, and also the logic building as well. It's not a small code, it's a good at least 20 to 30 lines of code. But one thing that you can see is a very good chunk of code from here to here, actually from here to here, or even from one line before that. Have.assign from there to here, all the lines have been duplicated over here. From software engineering perspective, you can have different opinion as definitely, but from the competitive programming perspective, what he did over here is basically he saved his coding time. He coded in such a way that he could easily utilize it over here, and together this accounts for around 80% of his code. Around 80% of his code is like he wrote something and then he just duplicated it, and the two parts he made so close. He coded for one part, the left part, and then he said, okay, for the right part, I'll do a similar thing. What did he do differently? He said, okay, I'll do from 0 to n, similar to what I did. He said that, okay, from the left, I will count how many elements I'm taking, similar to the I thing that I was tracking over there and what I stored in G over there. And then he did an interesting thing. He said, okay, have AI equals to true, while have AI or have car plus equals to 1. What is he doing over here? He calculated the MEX over here in the same way. What did he do over here? Over here, he is doing exactly what we had done before. That okay, go from one by one, and wherever you are seeing that it is not present, come out. But here, what did he do? He basically says, okay, at every point, see if you can proceed further from car. Is car present? If car is present, then see car plus 1. If car plus 1 is present, see car plus 2, and so on. In this way, he is increasing car. The moment he comes and says, okay, car equal to MEX, what does that mean? Car number of elements has been taken. It means that car number of elements has been taken. Car is the next element that is being searched. So before car, up to car minus 1, everything has been taken. That is the understanding. That is the summary of this. So, not very trivial to think, but my takeaway from this is that MEX problems are really quite common in Codeforces. And this guy has actually come up with some real good code, which can be reproduced in many MEX problems. MEX is a very popular, programming question type you can see in Codeforces. And this actually is a thing which can be reproduced, can be used in so many different problems. So this is something for which he probably didn't have to brainstorm at all. I feel certain that he has used it. Definitely, he might have used many other kinds of code snippets. This is not the only one, but I have a belief that he has used it in other kind of problems as well. This is indeed a good kind of thing. What you can see over here, it's a while loop. It will not keep on running. It's an amortized kind of thing. If it proceeds, we know that this will run for how many times? As long as that MEX is not found. So this loop overall will run for MEX number of times maximum for all the iterations of the for loop. So it's a good looking code. And what we can see with the second one, what has he done? In the second loop, he has said, okay, now I'll move from the end to the beginning. So from the beginning, he has found out the shortest one, fastest finishing one. The moment he finds MEX, he is breaking. And from the end also, now he'll find the shortest one. I hope you don't have the question in mind that, okay, what happens if it gets MEX? It will not get MEX. What happens if it crosses MEX? It becomes MEX plus 1. That will not happen because MEX, half of MEX won't be true. So the moment it reaches MEX, after that it has to come out of the loop and it has to enter this condition. Now he's coming from end to beginning. As a result, what is happening? It's a similar algorithm. So he's basically saying, hey, from the beginning, what I did was basically something like this. That hey, take the shortest from the beginning and then see whether the remaining one gives you all the elements, something like this. What he has done is, okay, take the first one and then take the second one. If the second one is bigger, if the second one is overlapping with this one, that means there are no two independent splits possible. There are no two disjoint splits possible, both of which contains 0 to x minus 1. There will be an overlap, so this will be a case of error. But if I say, okay, the second part finishes before or at that green line, so this line and this line either they intersect or this one remains to the right of the finishing line of the left subsegment, then we are good to go. We will say, okay, then you two can fit together. This is a good fit with this one. We can extend any of them. We can extend this one to fill the remaining elements. We can extend this one to refill the remaining elements. So that is it. That is a strategy which he has used. And rest of the thing is the same. 1 to a pref and pref plus 1 to g. Pref plus 1 to n. That is the same thing. So what do we learn from here is basically he identified an easy kind of code through which both the beginning and the end of the array, from both the parts, the MEX can be quickly obtained, and that's it. He finds out the minimum from the beginning, minimum from the end, and then he checks the overlap and he's done. So these two parts, from the beginning and from the end, he knows the same thing has to be repeated, and what we can see is maximum amount of code has been actually repeated from that part to over here. Some part of it is definitely which I have also attempted to do. So that's it, not much different. Now let us look at the next problem, problem C. Okay, this problem is interesting. It actually says we are given some pairs. There are n messages, each message contains a pair, one AI and a BI. And now the question says, now the time spent in reading the set of messages with these numbers, P1 to Pk, is going to be summation of API plus summation of BPI minus BPI plus 1 along this order. So it's basically if we pick up P1, P2, these particular indices, P3 up to Pk, this is the cost of those messages. I think that's what they have termed. Time spent reading those messages, and we have to find the maximum set of messages possible within a given time limit. So the time for reading these messages will be A of A of Pi, let's say A of Pi, where I goes from 1 to K, plus summation of relative differences of consecutive b terms, whatever we are choosing here. So b of pi minus b of pi minus I plus 1, the absolute difference of both. We will keep on doing this for I equals to 1 to k minus 1, k minus 1. So what are we saying? Between these two, whatever is the difference of b, between these two, whatever is the difference of b, between these two, whatever is the difference of b, between these two, whatever is the difference of b, all the b differences I'll be adding at the end. That is my final summation of this part. We have to keep this within a limit. We have to keep this within a limit, and we need to say, keeping this within the limit, what is the maximum k possible? So all this p1 up to pk we will be choosing. We will choose a k, and we will choose k different pairs. And then we have to do something like this. So we have to maximize the k. If it were only the first part, if I just had to do this, what would I do? I would say take the smallest one. Only for this part can I say we should take the smallest k, right? For this part, what should I do? For this part, I'll observe a bit more. Absolute difference, sum of absolute differences. If I say something like this, x1 minus x2 plus x2 minus x3. This will be minimum. I have to basically minimize this this sum so that my overall k can be maximized, so that I can take more elements. So my attention should be towards framing it in such a way that I can minimize it. For the same x1, x2, x3, if I say x1 minus x2 plus x2 minus x3, another is x1 minus x3 plus x3 minus x2. Which one will be more, which one will be less? How does it depend on their values? What we basically see is, let's say our x1 is greater than x2 and that is a greater than x3. So over here what we basically get out of that is x1 minus x2 plus x2 minus x3. x2 gets cancelled, so we have only x1 minus x3. So if we choose them in a concurrent, in this kind of an order, and basically take them pairwise, x1 minus x2 then x2 minus x3, finally we just remain with x1 minus x3. However, if I take in this way, I'll get x1 minus x3, x1 is greater, so x1 minus x3 plus x3 minus x2, this gets reverted, so it will become x2 minus x3, and so we will get x1 plus x2 minus 2x3. Now x2 minus x3 is greater than 0, x2 or we can basically end it over there. x1 minus x3 we had over here, and x2 minus x3 is greater than 0. So basically the entire thing is greater than 0. It is not optimal if we take it in different orders. If it is in this order, if the values are in this order, then basically keeping it in this sequence, or if it is in pure ascending order or pure descending order, keeping it in that sequence will optimize this one. So this is optimal. This follows, I mean, this will be minimized if my BPIs are increasing in ascending order. Increase in, I mean, they are in ascending order. BPIs in ascending order. All right. What next? Now, if they are in ascending order, then what will be this answer? This answer will be B of last element minus B of first element. So B of Pk minus B of P1. This will be the summation. Middle elements will all go away. They'll all deduct themselves. They'll all get cancelled, as we saw over here. x2 got cancelled. So now the question is, okay, second part depends only on what is the first and last element that I choose. In ascending order, let's say I'm choosing, if I'm choosing, let's say, the B's in the ascending order, then my attention should be only on the first and last values of B. And with those first and last values, which pairs will I choose? Those pairs such that I will only choose pairs from that B1. Let's say I'm basically choosing from a certain B1 So we have B1, B2, B3, B4 in the increasing order, let's say. This is sorted order. And I have A1, A2, A3, A4, A5, which is not in the sorted order. If I say, okay, I will choose 1 and 4, then out of these two elements, I will choose such elements that their summation will be minimum. The summation of the chosen elements will be minimum for the same amount of size. So if I say, let's say, I will have B5, this fifth one as my terminal elements. That means from here, I will choose the maximum number of elements with least sums. So here definitely you can sort if you have the luxury, if you have that time complexity allows it, then you can sort and you can select from the lowest elements from there. So for every pair, if you do that, if you say that, okay, for every pair, for each bi and bj, when they're in the sorting order, you will say, okay, for this I will consider all those AKs such that the BK lies in between BI to BJ. Then this BK is not involved. Then I can say for all those AK, you need the sorted order. You need the smallest ones. Those smallest ones will give you the best answer. So you can say, okay, first I can take A2, then I can take A3. If they can stay together, very good. If they cannot stay together, which one will I keep? The best one, the smallest one. So if A3 is better, A3 is smaller than A2, I'll say keep A2, A3, forget A2. Then proceed forward, then I can see, okay, A4 and A3, can they stay together? If they don't cross the limit, fine. So the overall summation will be, if let's say I choose A3, A4 over here, then for this B1 and B5, the overall summation will be something like this. A1, A5, these chosen elements from between, plus B5 minus B1, something like this. So, what are we basically seeing here? Something like this. Let's say I have some A2. So in sorted order, let's say we have a different order, B2, B3, B1, B5, B4. And for A's, let's say I have A2, A3, A1, A5, A4. Basically, I can say that, okay, if I pick this one, and if I pick another one, let's say this one, for that, I will now go and find out what are the minimum things you can obtain from here. That part is fine. So what can we say if I take these two, if I fix these two as my boundaries? This is in sorted order. This part is in sorted order. The B's are in sorted order. Now, if I basically say this, then my summation is going to be A2 plus A4 is going to be there, plus B4 minus B2 is going to be there. And what next? Plus, now the thing is empty. Now I can take anything from this part. So A3, A1, A5, A3, A1, A5, I can take any one of them. That has to be less than equal to limit. That is what I'll just keep in mind. It has to be less than equal to limit. So first I'll take A3. Let's say that A3 can fit in. I will take A3. Good. Next, I will try to take A1. If I can take A1, very good. I will take A1. Then I can try to take A5. Whether I'm able, if I'm able to take, very good. If I'm not able to take, by replacement, nothing is gained because two elements is the best. Let's say A1 I could not keep over here because A1 plus A3 plus the remaining things will give me greater than N. So what will I say? I can say, okay, compare these two, A1 and A3. If A1 is better, if you know that you cannot keep both of them together, if A1 is better, then you can strike it out and you can say keep A1 over here. Similarly, let's say you have some decent number of elements over here. You have kept A1, A2, A3, something like this. And now you're bringing A4. What will you see? You will say, okay, can A4 be present here? Let's say it tells you yes. It is fine, the summation is not yet exceeding. So you're fine, you'll just take A4 over here. What if it tells you that no, you cannot directly add over here because the summation will exceed the limit? Then you can say, okay, then give me the maximum out of this, that is the worst out of this. that has the worst contribution, because the maximum out of this will say, hey, for me, you cannot take other elements. The maximum one is the biggest barrier for us. So we'll sort of take the maximum and swap with that. Pull out that maximum, remove that maximum from there. Let's say A2 is that maximum, and then put A4 over here. A4. So the size doesn't change, but later on when an A5 will come, that will find it easier to enter if smaller elements are there instead of bigger elements. So at every point of time, what will we say? We'll just bring one element, we'll say, okay, can you increase the size by getting added? Till then you have the best size. So when I say this, A1, A2, A3, it is the best size up to that particular position, up to some A3. Now when A4 comes, A4 will say, can you take me? If you cannot take me, fine. We cannot increase the size. If you can take me, very good, increase the size, take everything. If you cannot take me, then show me your greatest element. It will show it the max, and if the max is greater, then we will replace it. What if the max is lesser? What if A4 is greater than the max? If A4 is greater than the max, if A4 is greater than the max of the elements already present, that means we know that this A4 can never find a position over there. Why? Understand this, that if I consider greater elements now, if I consider more elements now, let's say I'll consider A5, A6, A7, all those more A's I'll consider. What will happen? They'll basically come and say that if we are lesser takers, they can help increasing the size. This guy is already greater than all of these. Why would we ever try to take it in? We would not try to take it in. Now, one part of this is, if I do it for all possible Bi and Bj, what would be the time complexity? For all Ij, if I choose that, okay, for all Ij, if I say, okay, take Bi, Bj as the boundaries and then try the above things, then number of Bi, Bj itself is n square, right? Then, when you are running in between, you have to consider all the elements. We'll see the time complexity later, but you have to move from I to J. You have to consider all the elements, and that means putting into hash set or whatever you want, tree set or whatever, that will take you another big O n time. So from I to J, while you're moving through fetch all these AIs, A1, A2, A3, A4, this will take another big O n time. So for each pair of Ij, this big O n will be involved. So you will get a total of big O n cube. Got it? And most probably this will not be big O n, this will be big O n log n, because you're going to maintain a sorted set over there. So it is n log n, which means this will be big O n cube log n. Even worse. So let us see, does the time complexity allow? N goes up to 2000. 2000 cube is a bit bigger, but up to n square it is fine. So can we say, okay, for Bi, why should I consider every Bj separately? Let me try in a single run. So for this B2, I'll first consider this B3 as my terminal B3. Then I'll say, okay, move one step forward. Up to this B1, consider your terminal B1. Then the next step, consider up to here as your terminal B5. Terminal B, the last B. Then the next step, consider this as your terminal B. At each step, what will you do? You will say, okay, this is my last element. C, can you take this? And maybe few elements? Something like that. And can you get a good answer from there? That is what we will try to check. But okay, can we take this? Yeah, if it is my terminal element, then we definitely have to take this. If I take this, then from the set, does the set allow me to take this? The existing elements, whatever we have taken till now, does it allow me? If it doesn't allow me, okay, fine. Then I can't have any answer. Can't have any better answer as such. Why? Because let's say I have already got, for B1, I have already got few elements, few AIs up to there. So if I say, okay, if I cannot get in, that means the size is not increasing. It will be replacements. Replacements means there is no gain over there. So that's it. I'll just say, can I join? If it can join, very good. just increase the number, and so we just have to increase in the sum variable, and then that is done. So let us understand the implementation. I'll first go through my implementation. There's a C problem. Yes. What have I done? I have sorted this according to B. Where have I done it? In this pair class. I have basically sorted this according to B. And then if the B's are same, then I have sorted according to A. You can do this in any way. The greater or lesser doesn't matter because the algorithm has to work correctly for both the cases. Now going back. I'm sorting this over here. Next thing, what am I doing? I'm basically coming here and saying, okay, this is your I, the left boundary. For every left boundary, I'll start afresh. I will say, hey, pi dot a greater than L. If that first element's a itself is greater than L, then there is no choice, there is no chance, because we don't have negative elements to again bring it down. So if that crosses the limit itself, then just continue, don't waste time over here. That is a sanity check I did. You can try to experiment that if I don't do this check, whether it will run or not. By the end of the program, we will be able to realize that. What have I done next? I've said, okay, this is your starting sum. Then you will maintain a set to include the elements and, okay, now I've maintained a tree map. Why did I do over here? You can probably see that when I first solved it, when I first submitted, I got a wrong answer on pretest 4. The reason was that I used a tree set. I just maintained the values. What is this tree set? This would tell me that what is the minimum value, what is the minimum value, or what is the maximum value. Yeah, what is the maximum value that is contained. For maximum value, what did I do? I basically said, hey, put the negative one, because Java uses a min heap as a priority. Sorry, it basically uses a min kind of a structure. When I'm storing this, it's arranged in that way that only the when I say the first element, let me see. Yeah, when I'm saying the first element, give me the first element. It will give me the, the smallest one. That was the idea going in my mind. I actually could have done the last key as well, but I did some things. I stored basically the negative thing. It's the same thing. You can do it in the positive way as well. Not going much into that. What I've done, I basically said that store the frequency as well. This is needed because that's what gave me the wrong answer over there. If I just store the number and then I say at any point of time, hey, forget this particular number. Maybe that number was present multiple times. So over here, let's say this A3 and A1 was the same thing, same value. So both were 5, let's say. Now when A5 came, if you say remove the 5, it can the set can actually forget both 5. What happens as a problem? Later on when you will say remove the maximum, let's say A5 was only 4. When you say remove the maximum, it will remove 4 because 5s are already gone. It will remove both the 5s together. And so from C++ perspective, the best data structure to be used over here is, in this kind of a thing, the best data structure to be used is a multi-set. A multi-set would actually tell you that which elements are present, and it will store duplicate occurrences. If an element is present 5 times, it will store the element 5 times. In Java, we don't have that multi-set or multi-map. So I had to use something like this tree map to store the frequency. Next, what happened? So I'm starting with a count 1. Why? Because I've taken this ith element. So I'm starting with a count 1 and I'm considering it, right? Because this is the sum if I take only one element. Now, here I'm basically going through all possible ending elements. So I'm basically saying, okay, if j is something, I plus 1 is the starting point and whatever it is. So for j, up to j minus 1, we have got the summation. Then we are saying to that summation, we can basically add this, that okay, sum plus pj dot a plus pj dot b minus pi dot b is less than equal to L. What am I doing over here? I'm basically saying to that sum, add this pj dot a, add this pj dot a, whatever sum you have considered, whatever elements you have chosen till now, consider this extra element because we are choosing this particular pair as the ending pair. So choose both the a and b. This is the a part, this is the b's subtraction part. See that the summation is less than equal to L. If so, then you can directly combine it. Whatever was there on top of that, consider this element. So I'm basically adding that. And what am I doing? Get or default. Basically, see what is the frequency and add 1. You're increasing the frequency of the existing element or a new element by 1. Next, count plus plus. What does this mean? This basically means count of elements in that set. So in the best, I'll basically maintain this in that best variable, that what is the best count. Set.size also could have given me, but not set.size actually, the sum of the values of all the keys in this set or in this map. That actually would have given me this count, but I'm maintaining the count separately, plus plus minus minus I'll be doing. Next, what am I doing? Sum plus equals to this. Next, if the size of set is greater than 0, then I'll basically say, okay, you couldn't add it, that is fine, but can you replace? For replacement, you need at least one element in the set. So if there's one element on the set, then take out the maximum element, and then pj dot a, if your element is less than that element, then put it and replace that element, remove that element. So we will put our element and remove that other element. So okay, so we basically remove the other element. These three lines refer to that. I'm reducing the frequency over here. Don't just remove the key. I'm reducing the frequency, and then if it is getting reduced to 0, I'm basically saying remove it permanently. This is not needed as such, but just for sanity, just for removing unnecessary things, I did this. Now I'll say, okay, put the new element. This is how you put it, and then add to the summation. That okay, this is the difference. Pj dot a minus x. Why? Because I am adding this element and removing that element. So this is my ongoing sum. The sum I'm only considering in this case, because this is where, I mean, the best I'm only considering in this case, because this is where the set size is actually increasing. In the else part, I may be improving the set by taking in lesser element, but the set size is not increasing, so I'm not calculating anything over there. That's it. At the end, I'm printing best. So this is one thing that I've done. If we look at tourist solution over here, which he has done in 4 minutes. So I've been discussing this probably for 20 minutes or so, and he has done this in 4 minutes. Let us see what has he done. He basically adds the second element, I mean adds the first input AI to the second element of the pair and adds the second element to the first. Can you think why? From the C++ perspective, all of you who are C++, the interesting thing over here is, in C++, pair by default sorts by the first number and then by the second number. First number of the pair, this one, and then by the second number. So he knows he has to sort by B, same approach. So he has directly put pi.second over here and then pi.first. So whatever comparative thing I had to do over there, he didn't have to do because he's following the default way. So yeah, he just frames it that way. Okay, now he is just sorting it, same thing. And here also, pretty much for I, for every I he is considering every j. For every I, we are, as we define the tree map, he defined the multi-set. Multi-set is definitely the more accurate data structure. And now what he does is interesting. He starts the sum over here as 0. And then from j to n, he's just taking everything. So he's not adding the ith element over here. He's saying that from j, I'll be adding everything. As a result of this, what will happen? Look over here. He has fixed this. He is saying that jth element and ith element he'll be taking. So this difference is being considered. He is saying that remove this difference from the limit. The remaining limit we will track. To the sum, he is adding the jth element. Over here it is possible that I is equal to j. In that case this will have a contribution of 0, which we are fine with. But there is one fun to it. He then says, okay, up to j you have taken all the elements, you have taken the sum. Now if the sum is greater than limit, he has added that particular new element, which is the AI. Don't go by this second. Second means AI for tourist. So he has added it in the set, and now he's saying that summation, if your summation is greater than the limit, then keep on removing. So it's a while. It's a while loop. If the summation is greater than the limit, then he has said that remove that element. Forget that element, he is removing it from the set and he is also subtracting it from the sum. Now what is the outcome of this? It can happen that we will end up removing everything possible. It may happen that we'll end up removing this jth element, and that we can actually understand that that is slightly inaccurate. Why? Tourist is basically saying that okay, from I to j I am considering, and then there is an open pool. In this pool I have taken everything from AI plus 1, AI plus 2 up to aj. I've taken everything. But now maybe I'll be throwing out aj. If I throw out aj and say that the remaining ones are good, I'm still taking bi and bj. Then is this correct? The summation I'm taking, I'm not considering aj but I'm considering bj. I'm basically saying okay, bj minus bi is going to be there, plus the summation of the above ai's is going to be there. Is this correct? Is this a valid sum? Why not? Because this is not a valid sum, because if I'm taking bj, if I'm saying that bj is the end element, I'm taking bj, aj must be there. But tourist doesn't take that care. Tourist basically doesn't take that step to ensure that. He says, okay, let it get evicted. Let aj be removed if aj is really greater. So this sum will not exist. But does that affect the answer? No, because if let's say this sum is less than or equal to L, let's say we have counted this sum. This sum doesn't exist, but we have counted this sum, we have said okay, this set is correct. Well, this set up to aj minus 1 would be correct with bi and bj minus 1. May not be with bj, but with these two elements this would be correct. For that this would be valid, and bj minus 1 minus bi, this difference is lesser than this difference. This difference is lesser. Difference is lesser. What does this mean? That anyway I'll have an answer. Even if for this ij I don't have an answer, even if for this ij this is not the correct selection, for some I to j minus 1 I have an answer and I have already considered it. So this is not leading me to a wrong solution. I'm not counting something which will lead me to a wrong answer. So the same set, the same number of AIs has already been counted. So no worries. Similarly, if BI is gone, then if AI is gone, basically, let's say AI is gone. Basically, let's say these elements are there. AI plus 2, we can say BI plus 2 then is the new left boundary. This difference is even lesser. So this will be correct. So if I'm treating this as the correct, this will also be correct. So if this is possible, if this summation is less than or equal to L, that summation is also less than or equal to L. Which basically means in short that tourist's solution, this particular sum that he has created, this particular sum at any point of time, often is not a valid sum. But the way I understand is tourist is very well aware of it. That okay, even if this gives me different sums which are not existent, that will not give me wrong answer. That will not give him wrong answer. This is the reason. He is calculating it that okay, if the AI is lost, if the let's say the AJ is lost, if the AJ is lost, the BJ should not be there. But whatever is the new BJ, whatever is the new BJ after removing that AJ, that new BJ will definitely be better, and we have already considered it before, so no need to worry about that extra case. In this way, he just moves it in a way we can say he made the code look easy. There are many abstractions over here which slightly can be confusing why it works, but then sort of when you look at the entire thing, you can say he was highly calculative about what things he is skipping, and he was very careful about the thing that he is deliberately skipping. So again, we don't know how he has thought, etc., what steps he has taken, but this is the closest approximation we can make, and that's what I'm basically trying to do in this video. So he has fetched that element, he has reduced the sum, and then he has extracted that, removed that from the multi-set. Okay, what next? So in this way, the time complexity comes out to be n squared log n, which will pass the test cases. Then the problem D, this was an interesting problem. It basically says that some set of size n is given and some strange integer c is given. And now we need to calculate the number of pairs of integers such that the sum of those integers is not contained in the set, the difference of those integers is not contained in the set. X is less than equal to y. So basically, if I say that the set, this is one of the examples, c equal to 3. C equal to 3 means my xy can lie from 0 to 3, from 0 up to c, and x has to be less than equal to y. So basically, from 0 up to c, this is the condition. And let's say our set contains 1, 2, 3. That means, can we have 0, 1? No, because the difference 1 minus 0 is equal to 1. 1, 0 is not allowed because x is less than equal to y. Can we have 0, 3? No, because 3 minus 0 equal to 3, and 3 is a part of this set. So the difference of x and y should not be a part of the set. Now, can I have 1, 1? No, because 1 plus 1 equal to 2, and 2 is a part of the set. So what can we have? We can have something like this. We can have 0, 0. Because 0 plus 0 and 0 minus 0 both are not in the set. We cannot have 1, 1. We can have 2, 2. 2 minus 2 is 0. 2 plus 2 is 4. None of them are in the set. We can have 3, 3. I think these are the only possible answers. Let us see. For 1 to 3, yes, answer is 3. You can see 0, 0, 2, 2, 3, 3. Right. Now, how can we calculate this? The first way that I actually considered it, due to which I actually lost time in this problem, the first way that I considered it was in this way, that okay, the constraint tells me that n can go up to 3 into 10 to the power 5. N can go up to 3 into 10 to the power 5, which means that my x and y can go up to 3 into 10 to the power 5. Which means I can't consider all the pairs of x and y. I can't consider all pairs of x and y. I can consider all x, I can consider all y. These are the first two things. I can consider all x, and then I can consider all y. So I took the first thing, that for all the y, what are the sum of possible x? And that will be my answer, the number of pairs. So I said, okay, let us take all the y. For each y, we will try to evaluate it. So, I noticed something like this, that for a certain y, I can choose, for the x, basically I have to keep this in mind, that my y minus x should not belong to the set, and my y plus x should also not belong to the set. So let's say the set contains these elements. The set contains these elements s1, s2, dot, 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 sk. So what can I say? That means my y minus any si I cannot choose as x, right? That means x cannot be equal to y minus any set element, and I'm only interested in set elements that are less than equal to y over here. And over here, according to this, my x should not be equal to any set element minus y. Any set element minus y, where basically y is less than equal to si, or for all the si that are greater than equal to y. And what does this tell me? This basically tells me, okay, this will be a new set. Now y minus si basically tells me it will be a new set of those elements, I mean of all the y minus si's, and this will also be a new set. X cannot belong to this set of all the si minus y's. So x cannot belong to that set, x cannot belong to this set. So that is a set of all the y minus si's, this is a set of all the si minus y's. This is, let's say, set 1, this is set 2. Now, are set 1 and set 2 disjoint? If set 1 and set 2 have no common overlaps, I can say, okay, then the number of x I can take is basically up to y. I could have taken y plus 1 x, y plus 1 number of x. I can say, okay, remove the number of elements in set 1 and number of elements in set 2. But unfortunately, if there are duplicate elements in set 1 and set 2, if there are common elements, I have to say, okay, don't remove them twice, add whatever are common, set 1 intersection set 2. And this is where it becomes difficult. How to find these? Up to there it was fine, we could have done something. Y minus si, how many possibilities are there? Si less than equal to y, it was an easy calculation. But how many si are less than equal to y? Easy calculation. Similarly, how many y are less than equal to si? Easy calculation. The moment you are coming to this, that okay, y minus si and si minus y, like over here, if I take 2 minus 1 and 3 minus 2 give me the same thing. So for x equal to 1, x equal to 1 is invalid for y equals to 2 because of both this and this, because x plus y and y minus x both are present in my set. And that is the reason I'll come here and say, hey, this is difficult, this is hard to find. If you can find out, then very good, you can complete this solution in some manner. If you don't find out, if you're not able to find it easily, then unfortunately you have to think in a different way. This is where I pivoted. So for y also, I definitely, for y, this is what I found. For y, finding out number of x, this is the challenge I faced. That finding out this one. If I find out this one, then number of x I can find out for every y. Now the next part is, if I do all x, then also it's the same thing as a symmetrical thing. What is the other possibility I have? This is where I thought a bit, and then I thought, okay, all x difficult, all y difficult, what remains? All the elements of the set, because I'm dealing with x, y and all their size. So all the elements of the set, all the set elements, if I consider them, do I get something? So let us see. 1, 2, 3. 1, 2, 3 are my elements. 1, 2, 3. For 1, what can I say? How many xy pairs can give me a sum of 1? Can I say we can find that out? Something like this, 0, 1. Similarly, we can say that how many xy pairs can give me a sum of 2? I can say 0, 2, 1, 1. For 3 also I can say a similar thing. It's 0, 3, 1, 2, and so on. So this way, what can we see, that basically for any SI, my y can basically, or x, you can say x can go from 0 to SI by 2, 0 to SI by 2. So the possible number of x is going to be SI by 2 plus 1. We can say it's basically SI by 2 plus 1. For each x there will be exactly one possible y. So by this we can understand, here also we can see the same. So for 5 or 7 you can take an example and you can see, for 7 it will be 7 by 2 plus 1. Now with that many pairs we will get to the left. What are these pairs? These pairs basically are x plus y is equal to SI. How many such pairs are there? These many pairs. X plus y is equal to SI. So what are we considering? So basically for this, x and y both are less than equal to SI. X and y both are less than equal to SI, then this is my number of such pairs. Then if I look at the second possibility. Second possibility is that this is the difference. Then y is greater than this, x can be anything. So y minus x is equal to SI. And we know this thing x plus, y plus 0 and y minus 0 is the same thing. So we can say that y will be kept greater than SI, not greater than equal to. We will say y is greater than SI, because to prevent the duplication between the right and the left. Okay, so if y is greater than SI, that means for every y can I say there is a possibility. So if I have, let's say for this 3, what can I say? I can say that we can have 3 and 0. There is no other thing possible. For this I can say, okay, we can have 3 and 1, then we can have 2 and 0, so on. So if I had a bigger number, I could have said like 5, and let's say C was 10. I could have said, okay, 10 minus 5, 9 minus 4, 8 minus 3, and so on. So in this way, how many ways can I express it? For 1, what will be the answer? For 1 it will be 3, 2, 2, 1, 1, 0. So how many such pairs are there? What are these pairs? These are the disallowed pairs. We can't consider these pairs. So the sum of these pairs, or the number of these pairs, is basically going to be the number of y's that are greater than SI and up to C. So I can say the sum is going to be C minus SI. So each SI is basically giving me these many pairs. For each SI, this is the number of pairs. For each SI, this is number of pairs. SI by 2 plus 1 plus C minus SI. This is number of pairs that I cannot take. This is number of pairs that is disallowed. So I can just add it. But a bigger question, are there duplications? So we can see that between this 2, 0, let's say 1, 2, okay, I've taken this in the reverse way. Let me take this in the forward way. It is 2, 3, 1, 2, 0, 1. What I can say is that 1, 2 is common in this 1 and 3. So basically 1 is the difference of two numbers whose sum is 3. That is why 1 and 3 both are unhappy with 1, 2, and again I am recounting. Is there a way to help ourselves minimize the cost of this recounting? For this, turns out, easily I could observe a simple solution. We can say that, hey, if I notice for, let's say 3, or let's say 5, for 5, I'll notice the right ones. What are to my right? That is differences. Sorry, I'll consider the left ones. Let's say. So I'll consider that summation of which numbers gives me 5, left ones. So I'll have 0, 5, 1, 4, 2, 3. Yeah, that's it. Now if I see their differences, what do I see? 5 minus 0, 5. 4 minus 1, 3. 3 minus 2, 1. If you do this for any number, what you will see is that all the odd numbers will be covered. I think you know this, that if x plus y is equal to an odd number, then x minus y or y minus x will also be an odd number. So we are getting all possible odd numbers over here. You can do for a bigger number as well. What does this mean? This means that, okay, if I have counted this one, let's say, in the in the right of 1, let's say I've considered this in the right of 1, and I shouldn't count it. If I've considered this in the right of 5, then I shouldn't count it. Anyway, we are not counting for 0 for this y equal to okay, we are not basically counting this in R5. We have taken the measure already. Y is greater than si, so we don't need to worry about this duplication of 5. Basically over here it's R3. So if I take another example, let's say it's 11, or let's say 10. Now let's say before this we had some even numbers 2 and 6, which were there in the set. So what can we say? For the left we can say 0, 10, 1, 9, 2, 8, 3, 7, 4, 6, 5, 5. Now, what are the differences of these pairs? Differences over here is 10, then 9 minus 1 is 8, then 8 minus 2 is 6, 7 minus 3 is 4, 6 minus 4 is 2, 5 minus 5 is 0. We are getting everything. Now, 6 and 2 I have to ignore. 6 and 2 I should not recount. So I can say, okay, 6 and 4 already are covered by R of 6 and R of 6 and 2. It's already covered by R of 6 and R of 2 through summations, right? Through the differences, through the differences. So like 6, 4 is covered by the right of 2, because 6 minus 4 is equal to 2. Similarly, 2, 8 is covered by 6 in the right. 8 minus 2 is equal to 6. So we'll say, okay, this is being taken. So what matters to us? We can say, okay, this is the total number we would have expected in the left. This is the total number. The total number is 6, as we saw, C minus SI. Right? No, SI by 2 plus 1. So 10 by 2 plus 1. 10 by 2 plus 1 gives us 6, right? So we have 6 now. These two are already taken, so we will say whatever is the number of even numbers before you or odd numbers before you. For 5, we will say whatever is the number of odd numbers before you. If these two are there, we will say, okay, remove 2. Over here, 2 odd numbers are there. Sorry, 2 even numbers are there. So we will say, okay, remove 2. Remove 2, and then we get 4. So if SI is even, then we will say for left we will have the SI by 2 plus 1 minus plus 1 minus the count of even before, even till I minus 1, till SI minus 1. They are in sorted order, and if SI and R is definitely the previous thing, C minus SI. So SI equals to odd, same thing. L will be SI by 2 plus 1 minus count of odd till S of I minus 1. And R goes to, R will become C minus SI. That's it. So this kind of thing, the moment you get the formula, nothing else is left. You can see the solutions, they'll be the same things. I took more than an hour, close to 1.5 hours. I think most of the time was taken in the previous problem. So for this problem, I took close to 40 minutes, I think. Little less than that. You can see I changed approaches as well. So yeah. Okay. So once I got the approach, it's a small code. Yeah. And what you observe for tourist is that he basically completed the same thing in 4 minutes, and he has used the same solution. So it's a vector where he is storing the size, and then for all the i's he is calculating those two parts. This is the left part, this is the right part, and then he is saying, okay, now maintain the count, add this count of even or odd up to a point, and just basically add that to the answer. So if you are currently at an even number, then add whatever is the count of even numbers up to there. Now he's counting up to there. Why? Because he has kept +1 over here. This +1 we had not done, that is why we basically counted it up to I minus 1th point. But he's counting it up to the ith point, up to the current point. He's first incrementing it and then counting it because he has done this +1 over here. So yeah, either way you can do, it's basically the same thing. These ones will basically get subtracted due to putting this over here. That's it. Not much difference over here. The thinking was the main part. After that, implementation, definitely you can see in 4 minutes this guy has implemented it. And yeah, I think from the discussions I found that most people have found D easier than C. You can let me know which one you found easier. And finally, now we will look at problem E. Yeah, this is an interesting problem. It says that there are n courses. Each student is given certain courses, range of courses from LJ to RJ, something like that. So from a point to another point, all the courses have been given. And now, Jth student received grades this for their distance learning courses. Final grade is, yeah, LJ to RJ, what is given? Let me read over here. Minimum and maximum course numbers, yeah, right. So basically, question number D is something like this, that each course basically tells you what is the minimum that can be scored and what is the maximum that can be scored. And every student can score any number from this minimum to the maximum. Each course actually gives you that information. Now, for each student, you have another information that what is the range of courses that student can actually perform. So, let's say this is the range of courses. So, they can obtain anything from the minimum to the maximum in that course. For the I, the range basically is from the min of I to the max of I, which is basically as per the given notations, it will be something like from xi to yi. Yeah. Next, we have to say what is the maximum possible bitwise OR of the grades obtained. So from here, let's say the guy obtains grade I, from here grade J, and the last one, let's say, sorry, grade I plus 1 and so on up to grade J. So what is the maximum possible GI or GI plus 1 or dot up to GJ? For this, the prerequisite is you have to know a bit of bit manipulations to understand this bitwise OR, because the entire problem is based on actually looking at the bits very carefully. So maybe learn some bitwise things and then come back if you are a bit weak in that, or if you are still a beginner in that, and then you can follow this. Now, the thing is, what needs to be maximized? This thing needs to be maximized. The first thing that comes to mind is, okay, if you can choose the maximum scores, just choose those only. For every course that you have access to, choose the maximum scores over there so that your odd is maximum. Okay, usually that is correct. But what if two courses, one course basically has, let's say, two courses, one course has the minimum possible grade as 7, maximum as 8, and another course has the minimum possible as 8, maximum as 8. Now, if you choose the maximum, what do you get? 8 and 8. 8 or 8 basically gives you 8. If you choose over here that, okay, the student will get 7, And in the second one, the student will get 8. There is no choice because it can be only in this range. 7 or 8 is equal to 15. What does this mean? That choosing the lesser element gave us a better answer. Choosing a lesser element gave us a better answer. This is the maximum. So we have to maximize this, and so we need some better strategy. Each element can actually range. We have a range of choices for each position. The first thing is, let's say, if you have to maximize the result, what is the most important? Whenever we are approaching bitwise and we have to maximize the result, the most important is the leftmost bit. So, if these are your bit positions, for the leftmost bit, if you can bring a 1, that is the topmost priority, bring a 1 over there. That is the most significant bit, leftmost bit. From the left, if you can bring a 1 over here, that is your topmost priority. If you cannot bring a 1, fine, you have no choice. Then if you can bring a 1 over here, that is your topmost priority. So, if I say that, okay, let's say there is a 1 to 8. A particular cell can have 1 to 8. All the other cells have different kinds of other kind of ranges, let's say from 3 to 5, 4 to 6, something like this. Now, 8 basically looks like this, 1, 0, 0, 0. So the bit index 3 from the right is set in this case. And it is not set in any of the other things. 3 to 5, 4 to 6, it is not set. Before 8 also it is not set. So we can say here definitely this particular element gets used. The answer must contain this set. If we use this 8 in a different way, if we say, okay, no, we will not take 8, we will take 7, we will definitely get a worse answer. So this 8 actually ensures that we will get a better answer than anything else. So the first thing is that if a certain number comes with a very, the leftmost bit as set, no other number has that, we will take that leftmost bit from there for sure. After that, from 3 to 5 and 4 to 6, we can take whatever we want. Whichever one will give us the better answer, that we will take. So one thing is clear. The first step is secure the leftmost bit, or secure the bits from left to right, left to right. Over here also the strategy was the same, that you have 8 over here, you have 8 over here. From either of the 8, this bit must be set. So finally 15 actually looks like this, 1, 1, 1, 1. So this bit must be set by either of this or that one, or this one. This must be set. Then we saw that, okay, two different numbers are there. What did we see then? Okay, this 7, 8 looks something like this. 7 is 0, 1, 1, 1. 8 is 1, 0, 0, 0. What does this mean? This means that from here all the bits are different. From here all the bits are different. Now, if in the other numbers that are possible to be taken, 8, 8 for example, if 8 already sets this bit, if this bit is already set by this particular 8, let's say this particular 8, if that bit is already set, then I have the freedom about this bit. I don't need this bit anymore. If I don't need this bit anymore, then I can say I have flexibility about the next bits. Now there is a catch. I know that from here my bits are different. Bits are different, that is, there is some difference between the two, which means that the top one, the x, if I say this is xi, this is yi, xi is less than yi, I know that. There is a difference of at least 1 between them. So I know that yi minus xi is at least 1. If it is at least 1, that means if I subtract 1 from here, I basically get something like 0, 1, 1, 1. That entire thing is going to be greater than or equal to xi. I know this. Yi, basically what I wrote is, from this equation I wrote yi minus 1 is greater than or equal to xi. So this yi minus 1, 1, 0, 0, 0 minus 1 can actually help me get this important bits. So let me come differently. Let's say you have some numbers like this. If you have xi and yi, let's say initially some bits are matching. 1, 0, 1, 1, 0, 1. And then let's say bits are mismatching. So you have 1, 0, 1, 0, 0, and you have 0, 1, 0, 0, 0, something like this. Okay? At the end you can have a 1. Nothing changes. Now, other i's also we have chosen. This is for one I. This is for one course. Okay? This is for ith course. For this part, what should I do? Wherever I can use, I should use it. Like for this one, I should use it to fill up that particular bit if it is not filled. If it is filled, then what will I do? If it is already filled, if somebody else already helps in filling it, that is a very good, okay. I cannot, if it is already filled over there, I cannot say, okay, now convert it to 0 and have the entire thing, 0, 1, 1. I cannot do this because this is greater than or equal to, this is less than xi. This particular thing is less than xi. I cannot take anything less than xi. So I can say, okay, this part is static. I have to keep it exactly like this. This part is static. I can't do anything about it. I can't do anything about it. I can't change this to 1. Can I? Think it. For whatever I take over here, can I change this to 1? No. This part is like static. You can't do anything over here. So 1, 0, 1 and then something up to 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1 up to 1, 0, 1, 1, 0, 1, 0, 0. The first 3 bits cannot be touched. And that is the funny part. Okay, this part is interesting. Even if 10 different numbers have the same prefix, we can't do anything about it. We can't change that part. We can't change one of them to 0, 0, 0 and then 5 ones. We can't do that. If the numbers have to stay in this range, the first 3 bits have to stay exactly the same. Which means 1, 0, 1. This is guaranteed. In the answer, these 2 bits will be 1. That will be the contribution of this part. But next part becomes interesting. From this part where it is different, from the point where they are different, that is important to me. And which points are important to me? This point and this point, where basically I have 1 in the maximum number, in the greater number, in the upper bound of the range. Wherever I have 1, I'm interested in them. Why? Because I can easily convert them. For example, this particular one, I can easily convert this to something like this: 0, 1, 1, 1, 1. This one I can easily convert to 0, 1, 1. Now, you can ask this one also. I could have done something similar. Something like, here also I could have done something like this: 0 and then 0, 1, 1, 1. Why are we not doing that? Okay, if you really want to do it, why are you not doing this thing? You can easily take that. You might argue, why are we leaving this? We could have taken this and then it would look something like this: 0, 0, 1, 1, 1. That is from here 1, 1, 1. Okay, this lies in this range. We all know this lies in this particular range, right? 0, 0. Okay, no, it doesn't lie. But if, let's say, over here I had a 0, then this would lie in that particular range. So you can say, okay, if that was a 0, then this would lie. Why are we not considering it? Regardless of whether there was a 0 or 1 over there, regardless of that, this is already covered by this one. So if you want, take this one. If you have finalized to take 0 at the beginning, if you're not taking 1 at the first position, then go for this one. This will cover everything after that. So when will we skip this? When will we say don't take this one as it is? when this one is covered by something else, when this one is covered by something else, then we will say don't take the one from there. We will say don't take the one from there, take all the ones from here. So what am I basically saying? That if this one is already provided, if this one is already covered by something else, then take 0, 1, 1, 1, 1 instead of taking this one. That's it. So what turns out is that in xi and yi there is a part which is common. That common part has some limitations. You can keep exactly those things. Use them to fill up all the bits, whatever you can. Use them to basically fill up. You have to fill some bits. So use them to fill up some bits. Like over here, leaving the 5 over there, you'll fill this one and this one. Fill up those bits. If something else comes where xi and yi both have 1 over here, then again fill up this due to this. Do this. You can't change that. From the beginning, whatever are common in xi and yi, you can't change that to any other contribution. You have to take that. So take all those things. You may get some more things like this as well. Like this one and this one, maybe something like that. Now, whatever are over here, let's say over here you have a disagreement between two nodes. Or let's say this is what you got by filling using just those things. Just those bits which are common in xi and yi for all the courses that are involved, for the range of courses that are involved for a certain student. Now let's say for those courses, now for some course you see this cell has a disagreement. There is a 1 in the maximum and 0 in the minimum. Very good. Just take something like this. Say that okay, or if I take it in another position to be transparent about what happens. Let's say we have a 0 over here and 1 over here. So let's say this one. 0 over here, 1 over here. Xi, yi. I know that this is already a 1. So I no longer want to take this 1 as it is. I can say, okay, instead of this 1, do it like a 0, 1, 1, and continuous ones. So all those ones will come over here. This part will become full ones, which is the best. So you already had this one, and now you're filling all the remaining to the right with 1. 1, 1, and so on. So what was the logic over here? First, understanding that there are some static bits to the left which we can't control. So collect all the static bits and look at those right bits in a different way. Track those bits which are set in y. Among all those bits which are set in y, they may or may not be set in xi. But there will be some differences due to which this part of yi minus 1 will be less than, greater than, equal to this part of xi. That relationship will hold. So if I say this part is equal to xi dash, and this part is equal to yi dash, since the first bit itself is mismatching, I know that xi dash is definitely less than yi dash. We know this for sure. So when I do yi dash minus 1, I know this condition holds. So yeah, that's it. The first bit is mismatching, so in this way, yeah, we can do those things. What next? How will we implement it? So from any ith course to jth course, what are we looking for? Ith course to jth course, we want to see that, hey, from this point to that point, what is our bits occupied by those static bits. I mean the static bit positions. Static bit positions are first obtained. Static bit positions. And then we will see that, okay, in the dynamic bit positions, what are the count? The second step is dynamic, that is xi, yi. So the other bit positions we will now see. So for a certain bit position, let's say for kth bit position. Let's say A values, or let's say N1 values, N1 courses have static set bit. Static set bit means both, I mean, that set bit lies in the common part of xi and yi. So N1 courses and N2 courses have set bit in the greater number, that is yi, in the maximum part. Have set bit in the dynamic part, in the right half, in the non-static part, in the non-static part. N1 courses have static bit set, N2 courses have set bit in Y1 in the non-static part. Now if N2 is greater than or equal to 2, I am done. One will take care of that position, the other will take care of all the right positions. So this itself is fine for concluding one left shift of k. This actually means kth bit. So one left shift of k plus 1 minus 1, something like this. So all the bits from kth bit to the 0th bit, everything will be covered. If n1 is greater than or equal to 1, what value doesn't matter. Multiple courses can have a static bit set, but that doesn't contribute separately. So n1 greater than or equal to 1 and equal to 1 means the same thing to me. n1 greater than or equal to 1 and n2 is equal to 1 basically means the same thing. One left shift k plus 1 minus 1. And if I know that n1 plus n2 is equal to 1, that means one left shift k only. And if it is equal to 0, n1 plus n2 is equal to 0, that means n1 plus n2 is equal to 0, then no contribution. No contribution. If any of the bits to the left, they suddenly mask everything with 1, then it can be filled, otherwise not. So something like that. So yeah, this is a kind of a breaking point. If you ever reach this kind of a situation, where all the ones can be put, this is a breaking point. After this, you don't need to move to the right. So we are moving from the leftmost point to the right, and the moment we find that okay, we have got a breakthrough, now we can push ones all over. So this is a breaking point. We will say okay, we are done. All the things are done. It's already solved till the rightmost point. That's it. So there can be multiple solutions possible for this. I haven't yet coded it. Maybe in the next 1 or 2 days I'll be coding it, but it will be pretty straightforward from here, because the code will basically want two things. You have to store those two things, preferably separately. You can store that the static parts and the dynamic part. Dynamic part means there will be one line from where it is changing. From that time onwards, store everything in a separate structure. So in this way, one structure will tell you, okay, what is the bitwise OR, and the right part for that, one another structure will tell you for that non-static part, what are the contributions and the number of those contributions, we can say. So let us take a look at how Tourist has done it. There are multiple solutions possible over here. There was a hacking attempt, but the solution looked pretty correct. I don't think this solution can be hacked. So let's discuss on this, what he has done over here. Very good problem and very good implementation. What he did is he took, as we discussed, two different structures, always and extra. Always means the static part. Always and extra means which may or may not be involved. Next, for all the numbers, he is basically First taking the input and then processing them bitwise. He's going bitwise, and then for each bit he is fetching the whether it's set or not. If they are different, this is where it starts becoming different. This is where the extra part starts. Wherever it becomes different, the extra part starts. If bx is not equal to by, and he's breaking over here, so he just records, okay, this is different, this is the bit that is different. Let us see what he is doing. So extra I plus equals to 1 left shift j. That means the jth bit is different. And then from j minus 1 to 0, same thing he's doing. That 1 left shift k, those are all extra. So wherever the the maximum number has the set bit, he's marking them. Yeah, this is all extra. And we have seen actually how that actually. Yes, we have seen that in this example why those two purple colored things are only helping us. So that's what he is taking. Extra I plus equals to 1 left shift, yeah. And always I plus equals to bx left shift j. When are we doing this? Before breaking. When we are breaking, we are not doing this. Before breaking, we are adding this bx left shift j. Up to there, everything was, bx and by was the same for all the positions. Now when we are coming out, we are creating a segment tree on extra and always. So one day, when I'll have a bit more time, I'll share the basics of segment tree and I'll tell you how to solve different problems, easy to hard problems using the same segment tree structure. So these good programmers, these legendary programmers, they have these kind of snippets of segment tree which they can use, and with very small changes they can use it in difficult to difficult problems. So what has he done? He has created a segment tree. And what does a segment tree provide? In short, a segment tree will basically provide, depending on how we configure, the sum of elements in any range, the product of elements in any range, the minimum of elements in any range, the bitwise or whatever we want to store. And here we can say segment tree was not that needed. We just need a prefix kind of a structure. We just need to know, okay, from here to here, what is the sum? And if we basically store in a bitwise manner, if we store that, okay, this bit has occurred how many times up to each location in a prefix kind of a manner, it can be solved using that manner. So we could have done this in many different ways. We can do this using a segment tree. We can do this using a prefix structure. So basically a prefix sum kind of a structure, prefix sum of bits. So both are possible. We can discuss the comparison of time complexity between them. But first of all, this solution, which is about segment trees, SC, that is S of extra, and SA, S of always. For each query, we are taking the L and R. And then what is this guy doing? He is out of the extra, he's fetching the L to R. And from the always, he's fetching the L and R, only the value. In his segment tree, he's storing two things. One is the value, another is the over. What does over store? You can look at his code. I'll share in short. What over is basically, okay, let's take a look what over is doing. Yeah, while he's uniting two different parts, okay, that's how segment tree works. Two different segments while he's uniting, he's saying that if over here in the left part, if the over is set, or in the right part, if the over is true, then the overall over is going to be true. Otherwise, if a dot val and b dot val both have a common bit, both have some common bit. Now, what does this mean? For a certain bit, if you think, for a certain bit, the bit will be set in over if that bit occurs in the over of left, or occurs in the over of right, or occurs in the value of both left and right. And this is similar to your merge sort or that kind of an algorithm where you say, okay, the left and the right, and then there is the comparison between left and right. First, there are comparisons within the left, then comparisons within right, and then comparison between left and right. Here, what is happening is with over, he's basically storing that if there is an excess, if there is a greater than one occurrence of a certain bit, that is what he's storing in over. So, or what are the bits that are occurring more than once? He is basically storing that. So if it is occurring more than once in the left part, then good. If some bit is occurring more than once in the right part, then very good, that also. And if something is occurring in both the left and right, so the bit is neither occurring in the left part more than once, nor occurring in the right part more than once, but it occurs in the value of both the left and right. What is this value? Value is simple bitwise OR. Value is simple bitwise OR. So if it is occurring in both the left and right, that means it is occurring twice. So in the extra, basically he is checking that, hey, in this extra, for this extra, if from I to k minus 1 and k to j, in both of these parts, if my ith bit, if my jth, if whatever, let's say lth bit is set, and over here also lth bit is set, then when we will do bitwise AND this particular bit, here we'll have the bitwise or 1 we can say, or 2 we can say. When we'll do the AND, that particular bit will come up. The other thing is, if it is present more than once in the left, then also take it. If it is present more than once in the right, then also take it. So basically over is going to contain is a very good, very interesting mathematical formulation of telling whether a certain bit occurs more than once or not. Very good mathematical formulation. Now let's come down. What he is doing over here is, okay, in over he is basically finding out that thing. Okay, what he's doing over here is nd.over. nd.over means in the extra whatever is the over, or with that now he's doing the OR of the values of the two, nd.val and add, which means the values obtained from the extra and the always. So whatever are basically common. So if I understand correctly, if nd.over contains a set bit, nd.val will also contain that set bit. If nd.over contains a set bit, then nd.val also contains that set bit, but not the reverse. So either it is nd.over or it is that it is contained in nd.val also and add also. What does this mean? The first thing means that in our non-static part, in our extra part, we have more than one occurrence, and we discussed more than one occurrence means now we can overflow, we can use all the ones, we can pack the ones. Second part basically tells us nd.val and add. So basically if the first one is not true, then we are interested in the second part. This one tells that, okay, nd.val and add, nd.val is true and the first one is false, basically means that in the extra part it is present only once. Add equal to 1 would mean, in add if that bit is set, that means in the always part also there is one occurrence. So if in the always part there is at least one occurrence, in the nd.val if there is one occurrence, that means again we have two occurrences. And nd.over is basically that deciding factor. If it is nd.over, nd.val I think is probably not needed, because if I understand correctly, nd.over is it possible that nd.over will not have anything or will have anything which is not there in nd.val? Should not be, right? So nd.over contains those bits set which are present at least twice. So nd.val definitely should have that bit set. So I think this condition could have been written as nd.over. Maybe you can comment and let me know if you think differently. nd.val is increasing over nd.val or equals to add. Yeah, so nd.over should be a subset of nd.val. It should have a subset of bits of nd.val. That is my understanding. Yeah. And so we can say for nd.over, we can basically say this is a C++ function where he says that, okay, from the left find out or from the right basically find out what is the So what he has done over here is find out how many leading zeros are there. These are some C++ utilities. For us Java programmers, we mainly write for loops for these, but these are C++ utilities to basically go from the leftmost point to the right and say, okay, how many leading zeros are there? This automatically tells us. He's minusing that so that it gives us the position of the leftmost set bit in this nd.val or nd.val and over. I think nd.over is the right thing to be used over here. And then it is one left shift bit -1. He might have thought something and then this is correct, definitely this is correct, but I think nd.val and this part is not needed. But anyway, uh, we can maybe you can submit that and see if that works. So that is that part. nd.val or equals to, yeah, something like this. That is right. We are adding all the bits. That is right. So we are displaying it over here. Right, right. If it were not the case, what does it mean? That there was no set bit over here. nd.over, if this condition would be false if there is no set bit over here, then it is fine. Whatever nd.val contains, that is the answer. nd.val or odd or add. Yeah. So the space complexity or time complexity comes out to be, space complexity is big O n due to the segment tree, and time complexity comes out to be, over here there are some bitwise operations, so it's 30 into n, and over here segment tree actually has an n log n kind of time complexity. Yes, n log n time of a type of time complexity. So it is q into log n for every query. So building the segment tree will take big O n or big O n log n time depending on the implementation. I'm not going into that. This part will take big O n or n log n depending on how the segment tree has been built. And this part, each query should take log n amount of time. Yeah. So why log n amount of time is a very interesting discussion. Maybe I'll give a description of how a segment tree works one day, and from there you can solve different problems of segment trees. So yeah, so it turns out to be q log n plus n log n. That's it. So n plus q log n. Instead of log n, you could also have 32, that is log of a, if you followed a bitwise, prefix some kind of an approach, prefix sum of bits approach. But yeah, this is also fine. So that's it. We will take f maybe in a different session. I hope you found the problems interesting. So see you all in the next sessions. Let me know how it was. Let me know if you have any doubts. And see you all in the next contests. I hope you are enjoying participating in the contests and then upsolving. So see you in the contests and then in these videos for upsolving together. Thank you. Take care. Keep coding.